I should say I like to attend, but usually I can't because I have to take my kids to school at this time. So it's nice to be able to be here today. Yeah, so I'm talking about some work with Daniel Smertnig. He was a postdoc at Waterloo, and we were running a seminar on some problems from the book of Burstall and Reitnauer. And this is one of the things that came out of that. So I apologize for saying things that probably most people know, or maybe everyone knows, but I'll recall that if we have a field, and if we have a univariate power series, it's rational. Just if it's the power series of the expansion of a rational function, it's zero. So we don't want it to have any poles at zero. And this is equivalent to the coefficients satisfying a linear recurrence. I think this is all fairly well known. But one of the things that maybe people might not know as well is Pólya's theorem. So Pólya looked at the question of if I had take a finitely generated subgroup of Q star. So if you like, maybe think of a group generated by some primes, 2, 3, and 5, and look at everything whose numerator and denominator in lowest form can be written as a product of these. You can look at the rational functions whose coefficients are either zero or lie in a finitely generated group, fixed finitely generated group. And these rational series are much more constrained. And so this was first done for the rational numbers, and it was later extended. I don't know how to say Benza, Jo, and Bézevin did the general extension. In fact, Bézevin did it for D-finite series, and where you allow finite fixed sums of elements of G. But now in Pólya's honor, we call a rational series a Pólya series if there's a finitely generated group where all the coefficients are contained in either G or zero. And here's the sort of the big theorem culminating with the work of Bézevin. So if we have K as a field, and we take the power series expansion of a rational function, so we've got this rational series, and we assume that it's a Pólya series, so all the coefficients lie in a finitely generated group, then it has this very special form. Basically, the form is saying that it's a polynomial T, so up to a finite number of coefficients, it looks like one of these type of things, where it's basically just some sort of geometric series. And like I said, equivalently, you can say outside of the finite set, it looks like a geometric series. So let me just do an example. If we look at something like this, then you can see and if you look at expanding this, you can convince yourself that the coefficients are either going to be 0, 11, or a power of 3 times 2 to the I, or a power of 5 times 7 to the I. And this is going to lie in the group generated by what? 5, 7. So, or it's going to be 0. So we can work with something like this. And if you think about it, it gives this criterion. Pólya's theorem gives us a criterion that's easy to check if it's a Pólya series. If we have a series, an x to the n, then saying it's Pólya is saying there exists an R such that if an is not 0, then this lies in some finite set. So it's very easy to check this condition, right? It's saying there's some, in this case, I've got D. So for example, if you look at the Fibonacci numbers, 1 plus x plus 2x squared plus 3x cubed plus 5x to the 4, you can see that for any r, an plus r over an tends to an rth power of the golden ratio, which is not a rational number. And so in particular, the ratio can't lie in a finite set. So that's an easy way of seeing that the Fibonacci numbers generating series is not a Pólya series, although you could prove this directly, I suppose. Oops. Okay. let's do this. No. Okay, so this is, of course, very similar to the notion of regular series, which were introduced later by Aleutian Shalit. But we'll work in the realm of non-commutative formal power series. And again, I assume most people know this, but I'll just say it just in case. A series is rational. It's a bit like how we can form regular languages. So we're now allowing us to make non-commutative power series. And we allow the basic operations of addition, which would correspond to union when we work with languages, multiplication, which would correspond to concatenation, and then we've the Kleene star operation. For some reason, I want to do an example of this. So, okay, let's just do this example. If we look at something like this, if we look at our alphabet as XY, then if I take something like this, I can see that this is built up from these operations. I'm using multiplication, multiplication and addition, and then the inverse. And I can expand this out as a power series. And because it's non-commutative, I can't say this is x squared, y squared, or anything like this. And this becomes this. And I can see this is actually the same as this. So we get these identities, and these are how you prove a lot of identities in matrix theory like this, sort of Kaplansky's identity. One of the things we said, though, was that for the commutative rational series, we have this, the coefficients satisfy a recurrence relation, and Schutz and Berger talked about how we could extend this to the non-commutative setting. And in this case, we know the series is rational if and only if it can be, it has a linear representation. So I should say what we mean by this. And this is exactly like in K-regular series. You can see that we have this notion, but basically we have a homomorphism of monoids. So from our the free monoid generated by our alphabet to some matrix ring, and then we have a row vector and a column vector, and we take this product. And so because this is 1 by d, d by d, d by 1, we get a scalar when we do this. And we're just, for the purposes of this talk, we're going to let u, mu, v denote this representation. So this is really saying it's the map w goes to this. And like we said, this is connected to the linear recurrence because when x is a one-letter alphabet, of course, now our non-commutative series just becomes this rational series in one variable. And saying that we have a linear representation is saying that s of x to the n, well, we have mu of x, say, as a. So mu of x to the n is a to the n. And because we have the Cayley-Hamilton theorem, you know, we have some recurrence like this. And that's going to give us a recurrence on the coefficients. So and I should say that Reudenauer in his book with Berstel does the sort of similar thing with using Amatser-Levitsky theorem to get relations in the non-commutative world. So there is an analog of this. So I'll just recall that it's often useful to work with minimal representations. So if we can find a smaller equivalent relation that produces the same sequence that's smaller, then it wasn't minimal, right? So it's the analog of wanting to find a minimal automaton or something like this. And I should just recall, just for the purpose of this talk, that there is also a graph theoretical way of doing this with weighted finite automata. And so here what we have is we have a set of states Q, a finite set of states, and we have a function I, which is sort of standing for initial, and a function T, which is standing for terminal. So this is giving weights to the states, basically saying, instead of terminal being 0 or 1, now it can be some element of the field, and same with initial. And then what we have is an edge map, which I've written in this way, where we take a state Q, and we can think of this as being an edge from the state Q to the state Q prime, with the weight being like this. So the edge, so basically what we ultimately get is a directed graph where we have edges between, directed edges between the vertices, and the labels on them are letters of alphabet X, but the edges have a certain weight now, which is a value of K. So if the weight were 0, we just wouldn't draw it. It just won't contribute anything. So like we said, we say there's an edge with weight EP, with this weight, and we want it to be non-zero. And the state is called an initial state if I of P is non-zero, and it's a terminal state if T of P is non-zero. And then what's a path? It's just some just like we would think in a directed graph, it's just some path from our initial state to our terminal state. And we can assign the weight of this path as being the product of the weights. So that's why if we have a 0 weight, it won't contribute anything. So let's just very quickly just see why this is connected, in case people haven't seen this. I assume a lot of people have. But if we take, for example, what did I do as an example? If we take something like our U as being 1, 0, and here I'll take X to be the 2-letter alphabet, and then V to be, I don't know, 1, 1, and then UX is, let's say, this. Let's say we do something like this. Just by giving 2 states, oops, no. Just by making 2 states, let's call them E1 and E2. And I can think of mu of X as saying that, well, the 1, 1 entry is 2. So I'm going to say that if I encounter X on E1, I can go back to E1 with weight 2. And the 1, 2 weight is 3, so I can give that weight 3. And the 2, 1 entry is 4. So I can do something like this. And I can do something similar with Y, except here there's only 1 non-zero entry, and it's at the 2, 2. So we get something like this. And because my mu can tell me my initial weight, so I can assign mu of E1 is 1, because of the first entry, and I of E2 is 0, and T of E1 is 1, and T of E2 is 1. And then I can see that this automaton, right, if I look at paths from an initial state to a terminal state with weight, say, with label X squared, well, the only way to do that is I have to start here, and I can either go like this, or I can go like this. And if I go like this, if I first go like this and then go like this, I get weight 6. And if I go like this and then go like this, I get weight 15, I guess. And you can see that this is exactly the same as if I used this, well, hopefully it is. If I look at the 4, 12, I have no idea what I'm doing, actually. Let's see. But anyway, the point is that this whole mechanism is a way of converting linear representation to a weighted automaton, and you can see the converse. You can do the same thing. If you have a weighted automaton, you can make a row vector from the states and the column vector from the terminal values. And then you can make mu of x to be the matrix whose ij entry is just whatever weight we assign, where we are now allowing us to assign 0 values to. So that's how you go back and forth. So let's just recall an unambiguous weighted automaton is unambiguous if there's at most one accepting path for each word, and it's deterministic if there's at most one initial state, and for each pair p, x, and q, there's at most one q with this property. So what we're thinking of is when we have a weighted automaton, we're really thinking of the value of the word x, of a word, w and x star, is the sum over all the weights of the paths with label w that have this label w, all accepting paths. And unambiguous means there's just, it really collapses to at most one term. So that's what unambiguous means. So it's sort of unambiguous as to how we form this sum, right? How we determine this. So we saw that this, I can do another example here. This might be, it might be, I feel like I'm doing too many examples today, but I'm going to just keep going anyway. So here's an interesting example where we can see we get something unambiguous here, even though we have more than one initial state. So in this setting, this isn't deterministic how we've written it anyway. It probably is actually equivalent to something deterministic. But what we can see is that when we look at our weights, we're basically getting something like the two amorphs. And so I see that if I want to get to a terminal state, I have to end on state 1. And so if you give me a word like xyx, well, to end on state 1, that means I had to be going, I had to start here, then go here, and then end here. And there's exactly one path that I can take. So this is unambiguous. Okay, so all of this started with the work of Reutenauer, who introduced the idea of non-commutative Pólya series. And this is very nice work. So here we can work with a general integral domain R. And if we have a rational series, or if you like, you can think of a regular sequence, it's Pólya if the non-zero coefficients are again contained in a finitely generated subgroup of the fraction field. So it's, again, the coefficients are contained in G union 0. And accordingly, Reutenauer introduced this unambiguous rational series. I should say he introduced this unambiguous rational series and also showed that this was equivalent to to these unambiguous weighted automata. But his conjecture was that these unambiguous rational series should be precisely the same thing as the rational Pólya series. And just to recall, what unambiguous means is it's obtained from these operations again, but we can write it in such a way that there's a unique way to determine each coefficient. So again, I'm doing tons of examples today, but okay, that's okay. So let's look at a few examples. So again, we could do this example where we have our alphabet is XY. No, I don't want that. Let me do this. So on the surface, this doesn't look unambiguous. So it looks ambiguous, I guess. because this is this, and this is 2 plus 2yx plus 2yx, yx. But of course, as we saw, we could rewrite this as 3, as 2 plus 3 yx 1 minus yx inverse, and this is unambiguous. So now we see that there's exactly one way to form each non-zero coefficient when we expand this out, whereas in this form there were 2 ways for each thing bigger, for each yx, yx, and so on and so forth, right? We got one here, and then we got to form something formed here, but we see this is an unambiguous series in disguise. Another example, let's say we take just a one variable one, and we look at one. So if we expand this out, we get something like this. And this is not, I guess I should just say ambiguous, but I'm going to say not unambiguous. So this one is not unambiguous. Right? The question is, right, it demands a proof as to why this can't be written unambiguously, but intuitively it kind of makes sense that you can't separate this into something of the form something like this, right? Or right, we can't write it like this. That's an exercise, but basically in the one variant case, you can convince yourself that you really do have to get a Pólya series to be unambiguous, and you can see that this isn't a Pólya series by this criterion, right, where we know our coefficients are something like this, and again 2 to the n plus 3 to the n does not lie in a finite set. So for any r bigger than 1, this is not in a finite set, so we can see that this is not unambiguous. I'm going to now give our main theorem. So I want to make a few remarks. I'm stating the theorem. I didn't state a fourth equivalence because it didn't fit on the page, but maybe I'll state that at the end. And even though I'm stating these equivalences, most of these equivalences aren't due to us. Most of them are already due to Reutenauer. But our theorem is the following. Let R be a completely integrally closed domain. This is just sort of a technical thing that Daniel worked out. But for the purposes of this talk, the important thing to note is that things like Z or FPT or fields are all completely integrally closed. Completely integrally closed is something it's a little stronger than being integrally closed. And this condition is necessary for this theorem. There are counterexamples somehow, although I don't remember what they are. When we don't have something that's, if we have something that's just, say, integrally closed, but not completely integrally closed. For the purposes of this talk, though, we're just going to take R to be a field. That will make our lives much easier. And so let's say that we have our alphabet, and we have our non-commutative rational series. Then indeed we do get Reutenauer's conjecture that being a Pólya series is equivalent to being recognized by an unambiguous weighted automaton, which is equivalent to being an unambiguous series. And I should say that this was worked out by Reutenauer, as I mentioned, that the equivalence of 2 and 3. And the equivalence here going this way isn't bad at all. It's really this one that is sort of what we had to work out. So this was still sort of hard for us. So I guess I say here that the hard part is showing that this 1 implies 2. And again, really the hard part is the field case. So that's what I'll talk about. Once you do the field case, then you can just sort of do some commutative algebra to reduce to the completely integrally closed case. And I'm going to sweep those details under the rug. but I do want to say 3 implies 1 is more or less immediate. I think what I'll do is I'll talk about 2 implies 1, although it's more or less the same thing. So the idea is, right, if we have a weighted unambiguous automaton, so we have these states, Q2, Q3, and we have some weights, so maybe X, W1, X, W2, Y, W1, maybe we have a weight X, W3, then you can see that if it's unambiguous, if I want to know what the value of S of W is, well, it's just the weight of a single path, or at most one path. So it's the weight of a path. There exists at most one path P with label W, one accepting path P with label W. So either it's 0, either it's an empty sum, in which case we get 0, and that's fine, or it's just the weight of a single path. And we can see by how we define the weight of a path, it's a product of the weights. So this W of P is going to be in the group generated by these weights. And there's only finitely many weights. So we do indeed get a Pólya series, and you can do the same thing. If you wanted to work from the rational series point of view, you could just look at the set of non-zero coefficients appearing in your finite expression, building up your rational series, and let G be the group generated by those coefficients. And that'll be a finitely generated group, and you can show by an induction on the complexity that every coefficient lies in this finitely generated group. Okay, so now we finally come to some new part. I actually, I apologize. I think I did way too much sort of basic stuff at the beginning. Now that I think about it, now that I'm actually giving the talk. But I want to talk about something that we call the linear Hall. Actually, Daniel was the one who gave it the name linear Hall. I kind of like the name. But this was sort of the key tool we used to look at this problem. And I think it's actually a very natural tool that should have further applications, I think, in the study of rational series. But to motivate this, let me just take, probably people have seen some representation theory. We know that when we have a finite group, G, or Lie group, or whatever type of group, when we look at the representations, we have this notion of breaking it up into irreducible representations, right? So, and what that is really saying is that we can block diagonalize it. And typically, this is sort of the divide and conquer approach, where now we can we've broken up our representation into these irreducible building blocks, and we can study those. It suffices to study those. And we can do the same thing with linear representations, right? For instance, if I had something like this, mu is 1, 0, 0, and let's say mu of x was something like this, let's say my alphabet is xy. Oops. Then again, you could probably imagine that in this case, you can really break it up into a two-dimensional part and a one-dimensional part. Maybe in this case, the one-dimensional part doesn't really matter because we just have a 0 here. But you can see that you can convince yourself that we can break it up into smaller representations. Now, that's all good and well, but here's another example where we are sort of irreducible, but it's not sort of intrinsically irreducible. So let's say we had something like U is 1, 0, and let's say we again have the two-letter alphabet. And let's say V is 1, 1. Then you can see that if you look at U times mu of x, well, I'm just getting 1, 0. And if I look at u times mu of y, I'm getting 0, 3. And if I look at u of y squared, what am I getting? I'm getting 0, 3. Now I'm getting 15, 0. And mu of x squared, I guess, is still 1, 0. And what you can see is that if I look at the vectors I get, I'm either always on the x-axis or I'm always on the y-axis. And what happens is I end up here. Oops. So this is the span of 1, 0. And you can see that I end up here when I have an even number of y's. And I end up on here if I have an odd number of y's. So if I take the two-amorphs decomposition of x star, so I break it up into even number of y's and an odd number of y's, then I see that once I do this, now I can reduce. So if I restrict to these different languages, now I can reduce to one-dimensional pieces. So even though the span of all these vectors is all of C2, so it's not irreducible in the strict sense, we see there's a decomposition of our language so that when we do, it does become reducible. And so that's really the idea that's going to be key for us. So the linear hull is going to capture this idea of breaking up our representations. So this idea. And so to do this carefully, and you don't have to do this, but we're going to do this, and I'll explain why from the mathematical point of view, why we want to just do this. It's not that much work to actually do it, but we're going to put a topology on this. And I don't know what we call this, linear hull topology. But what we have is we have a finite dimensional vector space. And we're going to let this f of v be just the collection of subsets that can be written as a finite union of subspaces. So for instance, this would be in FC2, right? It's a union of two lines through the origin. And the important point is that if we look at this space FV, it becomes a Noetherian topological space. So in case, I assume people know what a topological space is, right? It just means it's closed under arbitrary, well, it's closed set, so under arbitrary intersections, finite unions, and the empty set and the whole vector space in there, that's okay. What does Noetherian mean? Well, Noetherian just means that if we take a descending chain of closed sets, it has to terminate. And this is an artifact of the fact that there's sort of an equivalent category. We can make a category out of this, and there's sort of a contravariant equivalence of categories when we work with some subcategory of commutative rings where everything is Noetherian. So this is not a hard thing to prove, and it's exactly the same proof as that there's a Zariski topology is a topology, and that's where the Noetherian comes in, because we get this Noetherian ring. But the great thing about having a Noetherian topological space when you argue mathematically is that you can always say, okay, let's argue by contradiction, assume what I'm trying to prove is not true, and then take something with a minimal linear hull. So because what this means is that because every descending chain of closed sets terminates, if we look at the linear hull, well, I haven't defined the linear hull, but if we look at sort of the set, if we have some sort of proof that we're trying to do for elements of FB, we can always take a smallest counterexample and argue by contradiction. So that's sort of something that's a very useful way of arguing, even if it's not that hard. Should I do an example? I feel like I've been doing too many examples. I don't know why I put in all these examples, but yeah, I will not do an example. I'll just go straight to the definition. So we can define the linear hull as follows. So if we have our representation as before, we can look at our vector u and multiply it by elements. So this is some matrix, a d by d matrix, and this is a 1 by d. And we get a set of vectors. And because we've got this topological space, now it makes sense to talk about the closure. And this closure is going to be some finite union of subspaces. And the point is that we're going to be dense in each of these subspaces. So we're going to have lots of points in general if we have a plane or something like this. And notice we can define the right linear hull as well by working with this and taking the closure. Okay, so now I will do an example. Let me do the example we were doing before. So we have something like this. Let's say our x is xy, and mu of x is something like this. And let's say that v is 1, 1. And if we look at the left linear hull, I think we started to work this out. We saw that we got 2, 0. Mu of y we said was what? It was 0, 1. And I think we sort of convinced ourselves that the linear hull ended up, we always got a vector here on the x-axis or a vector here on the y-axis. And we were sort of dense. We got lots of vectors here and lots of vectors here, so we couldn't break it up into smaller spaces. So this is the left linear hull. And if we look at the right linear hull, it's a little different, right? If we look at v, that's 1, 1. And if we look at mu x v, now we're getting 2, 3. And if we look at mu y v, we are getting 1, 3. And it's fairly easy to convince yourself that we're always getting something non-zero in each coordinate. And I claim that the right linear hull is all of C2. And what's the proof? Well, if it weren't, it would have to be a finite union of lines, right? We're working in a two-dimensional space, so it would be some finite union of lines, L1 through LS. And because of the nature of the linear hull, we see that if we're in one of these points and we multiply on the left by mu of x, we have to stay. We have to remain in one of these. So mu of x, Li, is some L sigma I. In fact, it's a permutation because our mu x is invertible. And so that means that there's some power of x that has to fix all these lines. It doesn't fix them pointwise, but it leaves the line invariant. So it takes the line to itself. And that is saying that Li is an eigenspace for mu of x to the n, which is what? Mu of x to the n is 2 to the n, 0, 3 to the n. And you can see that the only eigenvectors for this are the x-axis and the y-axis. So those are the eigenspaces for this matrix. But we just saw that we always get something non-zero. So we know we're not contained in the x-axis or the y-axis. So we know the linear hull has to actually be the whole space. So the left linear hull and the right linear hull can be very different. The left linear hull can be one-dimensional, and the right linear hull here is the full space. But you can sort of play off linear hulls against each other, and you can always work with the one that's most favorable for you. So you can always sort of work. We could reduce to the one-dimensional case in studying this by working with the left linear hull and not have to worry about the full two-dimensional space. So the linear hull allows us to break up these supports where we have this sort of strongly irreducible idea where we can't sort of break up our language any further and get smaller spaces. So that's what I mean by this strongly irreducible. And this is, I think, sort of the right notion of irreducibility when studying these rational series. And one of the great things about Pólya series is, and sort of deterministic and unambiguous automata, is that you can really detect it in some sense by saying that the linear hull, after working in some sort of sense, can be sort of reduced after putting it in some normal form into one-dimensional subspaces. So that's sort of the power of the linear hull and the connection with Pólya series. And the idea here, it's easiest to see this in characteristic zero, but what we have to use is we have to use something called the S-unit theorem. So the idea is if we have a linear representation, again, we sort of can work with the linear hull, and we can always sort of work, after refining, we can work in a space where we're sort of strongly reducible. So we can always reduce, and we can reduce to sort of minimal linear hull by this Noetherian property. And if you do all of these reductions, you really can reduce to the case where your vector has no zero coordinates. Because if you think about it, if you had a lot of zero coordinates, you would really be lying in some sort of hyperplane, and you could again reduce. So you can sort of reduce to this case. And you can reduce to the case where your matrix, all the entries are either zero or in the group. And the same thing with this. So if I think about mu of W as being some vector where all the entries are in G union 0, then when I multiply this by V, I'm really getting something like this. And the Pólya condition is saying that I want this to be in G union 0. So that's sort of what happens when you reduce to a minimal linear hull and do this argument. And like I said, we can work with the what's called the S-unit theorem. So what is the S-unit theorem? The S-unit theorem is a very beautiful theorem. Who is it due to? I'm not sure. It's probably Averza and Giori, maybe Schmidt. A lot of people did work on this S-unit theorem. But the point is, this is the sort of the most general version. If we have a group that's finitely generated, a subgroup of the multiplicative group of a field, and it's important that we have characteristic 0, then there are only finitely many solutions to the equation Z1 plus ZD equals 1, where we insist that all the entries are in G, and so that no non-trivial subsum vanishes. And I guess examples due to Leck from the 50s show that you need the characteristic 0. Characteristic 0 is important. For instance, if I look at the equation x plus y equals 1, and let's say I work in the field FPT, and I take the group generated by 1 plus t and t, then you can see that 1 plus t to the p to the j, let's throw in minus 1 here as well, minus I'm always getting 1 because we're in characteristic p. So this is 1 plus t p to the j. And I can see that that's infinitely many solutions. So characteristic p is a little trickier. Nevertheless, we can deal with characteristic p, but let's worry about this later on. Let's talk about why this theorem is relevant to us. So we saw before we were getting equations like this. And we were getting lots of them, Z1 plus ZD. Well, what happens is we can look at where case 1, we can look at some subsum vanishing, some proper subsum vanishes. And that is really some sort of hyperplane or some sort of, hyperplane condition. And that allows us, we can reduce the linear hull in this case. So if we restrict to the cases where a fixed proper subsum vanishes, we can reduce to a smaller linear hull and get the result. And of course, there's only finitely many different possible subsums that can vanish, so we can do that for each of them, and we can reduce in those cases. So we can reduce to no proper subsum vanishing. And then what happens is, well, we can either look at this or this, but no proper subsum vanishes. What we know is that there are really only, up to scaling, only finitely many solutions. Because if we have a g here, we can divide by g, and we can always divide by the first non-zero coefficient. And so up to scaling, there's only finitely many solutions, and that's saying that we have to lie, that Z1 through ZD lies on a finite union of lines. And that's the same thing as saying that our linear hull is a union of lines. I guess I should say one more thing, that we are done once we reduce to linear hulls being dimensions being lines, because like I said, we can reduce to the case of a line, and then that is just saying that mu is mapping X star. We were mapping to D by D matrices, but now we've got a line, so it's just 1 by 1 matrices, and mu and v are now in K, they're scalars. And if we look at what our word is, we're getting mu is just u. Is now an element of K star, or in 0. And this is just a product of these weights. And so there's only finitely many different weights, so it's in this finitely generated group. So that's how we can reduce in this case. Like I said, in positive characteristic, we don't have this S-unit theorem, but there's this nice work of Dirksen and Masser. They have an S-unit theorem in characteristic P. And if we go back to this example I gave due to Leck, you'll notice that really we only have finitely many solutions when we work up to the action of the Frobenius map, where we apply a p power. So Dirksen and Masser says in some sense that when we do the S-unit theorem in characteristic P, we do get a finiteness result up to some action of Frobenius. But the action of Frobenius can be a bit complex. So that's what we get. And so in particular, we know that if we work with some notion of height, we don't get that many solutions to the S-unit equation. And we can work with that because we actually can show we get lots of solutions when we work with the linear representations. So even though we don't have the S-unit theorem, we can still sort of reduce to this one-dimensional linear hull argument. In more recent work, Daniel and I, we have found an algorithm to compute the linear hull of a representation. So we saw people were sort of, people in sort of theoretical computer science, we saw sort of picked up this linear hull stuff and were working out special cases. So we decided to do this. And so the question of whether a weighted automaton is equivalent to an unambiguous or even deterministic weighted automaton is decidable, because we can use this sort of linear algebraic approach to computing the linear hull. So that was one thing. I did want to say something. I'm running out of time, I guess. I did want to say one thing about the connection with Pólya series, Pólya's theorem. So this again is connected with work of Schütz and Berger and Reitnauer. That if we look at the non-commutative world, I'll just say this. If we have a group generated by finitely many elements, and let's say for the purposes of this example that it's just the free abelian group on lambda 1 through lambda s, then that means that if we have a Pólya equation, we can write a non-zero coefficient in this form. And we can ask, what about these AIWs? Well, these AIWs are, of course, integers, but they're going to now be, this is going to be a rational series. The only other condition needed is that these are sort of linear bounded. They're not growing very quickly in terms of the length of W. So they're linearly, what's called linearly bounded. So there is a sort of nice analog in terms of the concrete description of Pólya. Anyway, that's all my time, so I'll say thanks. That's the end of the talk.
Thanks a lot, Jason. Does anyone have any questions? Yeah, Christoph.
Yes, thank you, Jason, for this very nice talk. I just wanted to congratulate you. I already congratulate very much Daniel.
Yeah,
and it was an old conjecture. You didn't mention this. I worked on this in '78. I think published it in '79, and you mentioned what I have done. And the hard part, which is really hard, I was completely